Hello, friends. Wish you a happy new year to all of you who have joined. Thank you, everyone, for attending the first webinar of this year, Mastering the Thread Dump Analysis, 9 Tips and Tricks. So, friends, if you have any questions during this session, feel free to put it in the Q&A section or in the chat. I will answer them towards the end of the call. Okay. Having said that, let's get started. Okay. So, what is a thread dump? Let me start off with the question. So what is a thread dump? So friends, thread dump is nothing but a snapshot, or you can think it as I'm taking a photograph of all the threads that is running in your application. So it contains where the thread is executing, what logs it holds. So that's what it contains. We'll look into what goes into thread dump in the next slide. But before that, I just wanted to share this very interesting perspective. Friends, threads in general, they are like kind of the blood system of our application. They are kind of a blood system of our application. See, our application talks with multiple backend system of record. There are so many different channels in which our customers are communicating to our application, and the application talks with JVM and then operating system. It runs in a cloud infrastructure, right? It works with multiple components. But if there is any problem anywhere, it's going to be reflected in the threads. Very similar to, see, the blood. If there is a problem in your liver, or if there's a problem in your kidney or lungs or anywhere, it's going to be reflected in your threads. That's why the doctors draw the blood samples so that they can see what's going on. This is very similar. If a backend is slowing down, or if there's a network distortion, or if garbage collection is stopping your application, anywhere any problem happens, the distortions will be observed on your thread's behavior. So when we take the thread dump, which is basically a photograph of all the threads that is running in your memory, and if you can pay close attention, we can solve most of the performance problem. I will not say all, but most of the performance problems that we are confronting in production, we can solve it. So having said that, let's see what goes into a thread dump, right? What information is present in a thread dump. See, friends, this is a sample thread dump. See, at the very first element, what goes into a thread dump is the timestamp at which the thread dump was taken. In the next information, it shows the JVM version information, whether it was running on a 32-bit, 64-bit, or whether it was running on a client mode or a server mode, right? We get those information. And then the next is, we are going to see this kind of a segment, right? This segment tells the details about this particular thread, invoice thread AA996. Say if your application is going to have like, let's say 300 threads, you're going to see like 300 segments printed within your thread dump file, right? And thread dump is a very simple text file. You can open it in a text editor and you can look into it. So let's zoom into just this one particular segment. What is there for one thread? Okay, let's look at this. So let me enable the pointer so that I can precisely point and show you. Okay. So the first element in this thread segment, what you're going to see is the name of your thread. See here, it is called as invoice thread A996. So this is the name given to the thread by the developer. See, as developers, there's a thread.setName API is available, set name. So I can use that name and then I can set it. I can invoke that API and pass whatever the name I want to give. So then that information will be reflected here. And then the next element is the priority. A thread can have a priority anywhere from 1 to 10. 10 being the highest priority and 1 being the lowest priority. So whenever there is any contention, the threads with highest priority gets chance to run first, then the low priority ones. And then the next is the thread ID. So this is the ID given by the JVM to our thread, right? So, right, JVM not to keep track of all the threads. It gives ID to each thread. So this is that JVM thread ID. And then next is NID. What is this? Native ID. See, if you see, my friends, thread is nothing but at the end of the day is an operating system resource. It's a kernel resource. So kernel, to keep track of all the threads, it uses this native ID, right? So it is this ID. So if you want to use some kind of a kernel level tools to look at what the threads are doing, then this is the ID that will be reported in those kernel level tools, right? So the way to visualize this is, already there is kind of we are having three IDs. One is this name given by the developer, thread ID. This is given by the JVM. And the third is a native ID, which is given by the operating system. The way to look at this is, it's very similar to our naming convention. See, my name is Ram Lakshmanan. So this is name given by my parents. Thread ID, you can visualize this kind of, say, suppose I have a driver's license. I have a California driver's license, right? So that is given by the DMV, Department of Motor Vehicles. So similarly, I also have a social security number given by the federal government. But it's at the end of the day, everything is pointing to me, right? So that's one way to look at it, okay? And then the next one is the state in which the thread is running. A thread can be in 6 different states. We'll talk about it a little later. So what state it is. So that's what reported here. And the 7th one, and probably this is what the most important one, is the stack trace. It is a code execution path. So you want to read it from the bottoms up, right? So this says, this is where the thread started out first. This is the very first method the thread executed. It was on the run method of the thread class. And from here, it went on to execute this method. And then it went on to execute this method. So it progressed. And at the time of taking a thread dump, this is the final method it was executing. It was the last executed method by this thread, right? Friends, that's all the information which is there in the thread dump. Nothing more, right? It just shows timestamp, JVM information. Each thread is going to have this. That's all. Nothing else. But friends, with this, just with this information, we can do magical things. We can uncover several production performance problems. So that's what we're going to be discussing. Let's discuss. But before discussing that, let's see how you can capture a thread dump. How I can capture a thread dump from my application. Friends, here are some of the options. I've given like 8 different options using which you can go ahead and take a thread dump, right? But I would recommend, these are all good options, right? But my most favorite and what I will recommend is using this open source script. See, friends, this is an open source script called a YC data script. So you can trigger this script like this. You can say it is platform agnostic. It can run on any flavor of Linux, Mac, Windows. So you can say YC-P and give the name of your process ID. When you trigger this script, the script is going to capture thread dump. Actually, it's going to capture 3 snapshots of thread dump. Along with that, it's also going to capture other artifacts. It's going to capture a 360-degree artifacts, which is needed to troubleshoot a production problem. See, friends, thread dumps are very vital information. But production problems, especially in the modern environments where it is getting serverless, containerized with Kubernetes, troubleshooting is becoming harder and harder. The troubleshooting was 10 years before was a lot more easier than what it is today because environment is getting complex and complex. So having a thread dump is definitely a very good thing we need to do. But along with that, if you can capture other comprehensive data, it's going to make our troubleshooting very effective. So what does the script does is, the script captures all these 360-degree data, bundle them up, and generate a zip file. So once you have the zip file, then you can do an analysis offline, right? Okay. So this is, I would highly recommend using this script to capture the thread dump. Okay. So now, once you have the thread dump, how you're going to analyze? Friends, you can very well use the text editor, open it up and look into it, which is one very good option. Please do, I encourage you to do it. But there are some tools are available in the market that you can look at it. So there is a fastThread, Ycrash, which is both of them are made by our company. There's also IBM as a tool, right? You can take a look at it. But for our discussions today, I will be focusing on how to do this analysis with fastThread and also the manual approach. So if you don't want to use the tool, you can still analyze manually. So we are going to discuss that. Okay, so now let's analyze, I'll just show you how to do a thread dump analysis. So now, so let's go here. See, this is that fastThread tool. It is available online, and it is also available as an on-prem installation. There is a lot of companies classify the thread dumps as a confidential data because a production artifact, they don't want to upload on the internet and processed on the external servers. So there's also on-prem installation where you can download and install the tool locally and run it. So now let's use the tool, and then I'll do the demonstration, right? Okay, so now friends, let me open a thread dump file. So I do have a lot of thread dump files. Say, here is one of the thread dump file, which is a very unreadable cryptic text. So let me upload this thread dump file into this tool. There is also a automation approach, and there is also can copy and paste, but let me just upload it as a file. So now once I upload, the tool is going to process, and then it's going to display that thread dump file as a result, as a report for you. So if there are any warnings, it's going to report it as a warning here. So you can look at what's going on. But I'm not going to, let's talk about this a little later. Okay. So this is how you do the thread dump analysis. Now let's zoom out. And now what I'm going to do is, this is where I'm coming to the core of this webinar. I'm going to be sharing with you 9 tips and tricks that you can use to analyze the thread dumps. Okay. So let's get started so that you can unearth the problems pretty fairly quickly. So friends, the first tip that what I want to share with you is, look at the last executed method of each thread, right? So we saw in the thread dump, it's going to show what are all the threads. Each thread is going to have one segment. Look at the last executed method and group all the threads which have ended up in that method. So what do I mean by that? If I show you a real example, it's going to get clear. But friends, typically what happens? Whenever there is any performance problem or whenever there is any production problem, there's a bottleneck in your application. If there's a bottleneck, then what's going to happen is multiple threads. Our application has hundreds of that. All the threads are going to navigate and they're going to be stuck on that same bottleneck, right? So that means they're going to be ending up sticking on the same method. So if you start to look what is the last executed method of all the threads and where they are, if there is several threads, they're going and accumulating at the same point, that means that's a concern. That you need to start looking at it. See, there is this saying, right? All roads lead to Rome. So similarly, when there is a bottleneck, all threads, most of the threads in the application is going to navigate and they're going to be stuck on that one particular bottleneck method. So you want to look at all the threads, the last executed method, and group them. So now, here for this, I've got a real thread dump. This is a real problem that happened in a financial institution in North America. So that application became slowed. It started to slowing down. It was not responding to the request that was coming in. Now we are going to look at that thread dump, right? Let's look into that thread dump analysis. Okay. So friends, what the tool does is, if it detects any problem, it's going to report as a summary. Okay, here are all the problems and gives a level. If the level can be warning, danger, or fatal, right? Here it has reported like 3 warnings. Now, if you see this application has somewhere like 191 threads. Let's look at that. Now, here there is a section called, so you can do this manually. Totally can do this manually, but it's just a little bit tedious for you to do. So that's what the tooling does. So here, there is a section called last executed methods. See, out of those 190 threads, 87 threads have ended up in this method. Look at this. It says 46% of the threads in this application has ended up in this method. And the tool detects what's going on and then reports here. But now, it's asking to examine the stack trace. See, multiple threads ended up, so it raised a warning. Now let's go ahead and look here. Okay, friends, look at this. This is one of that 87 threads which has ended up in this method. File dispatcher IMPL read 0. This is from that the JDK package Sun. So let's look at where the thread started. So you can see this application was running on a WebLogic server. You can see it is coming along. It is executing the WebLogic code. It's now going. Now you can see based on this tactics, it's entering into an Oracle JDBC driver. Now it's making an Oracle JDBC call. Now it's stuck there. So what does it tell? What does it tells us is this method made a call. This thread made a call to Oracle database, and now it didn't get a response. So it's stuck there. Now let's look at another thread. I'm going to click on some other thread. This is a different thread. Look what this thread is doing. So this thread is also, it's in the WebLogic server, starting with here, and now it's progressing. And now it is also, you can see it is also going through this Oracle JDBC driver. And after it also end up in the same method. File dispatcher IMPL read 0. So it means what? This thread is also ending up in the same method. So like this, you can see 46% of this application threads ended up in this method. So this is telling, if you see all of them are going through this Oracle JDBC driver. So this is telling that Oracle database to which this application is, so I see Sumant is raising a hand. Sumant, I think you can put the question. I will respond at the end of the call, right? Okay. So you can see the threads are going to Oracle database, and there's some slowdown is happening in the Oracle database side, Oracle RAC cluster. So all the threads are going and getting stuck there. Okay. So this is going to be even more beautifully visible. If you see at the bottom, there is this flame graph section. Let's see. There is this flame graph. See, friends, our thread dumps, when we capture, it's going to be at least few hundred megabytes file or few megabyte file. Because thread dump, we have hundreds of threads, each thread is going to have a segment, so it's going to be pretty lengthy file. So this flame graph consolidates your entire thread dump and presents it for you for consumption in one single view. In one single view, I can see what's going on in my thread dump. So this is that. Let me help you to show how to read this dump. Okay. You can see this is where all the threads are starting, right? There are 174 threads. From here, 96 threads, you see the thread count on the right side. 96 threads went on to execute this particular WebLogic work execute thread run method. And they are all progressing. From this 96 threads, 31 threads went on to execute this particular tower, and 64 threads went on to execute this particular tower. And you see it is also color-coded. What are the different packages are in different color codes. Here you can see, here there is this, see I put, since this data is sensitive data, the XXX, it is that financial institution that has been masked. So you can see 14 threads from this application are going through this update workflow method. And now we can see from here it is going on this Oracle database. And now you see the last method they're executing all these 14 threads where that file dispatcher IMPL. So this is an Oracle call that is made, and it's getting, since Oracle is slowing down, they're not getting response. 14 threads are stuck here. Now you see this is a different code path. This is a different code path. Even this code path is finally ending up in the same method, file dispatcher IMPL. See the way to visualize this, our applications have multiple transactions, right? Let's say I have a login, sign on transaction, funds transfer transaction, account overview transaction. I have multiple transactions in my application. If my backend system of record, the primary system of record is slowing down, it does not matter which path I enter my application. Finally, I'm going to be stuck in this net IMPL method. You can see this happen. See, this problem is going to become very evident if I reverse the flame graph. See, let's say I reverse the flame graph. When I reverse, you see now these are all the different entry points to my application. I reversed it. See, now these are all the different entry points. These towers all indicate different transactions. If you see finally, like how different rivers comes and then they connect with the ocean. That's what is happening. Different transactions are coming, but finally you see they are all merging on this Oracle call because Oracle is slowing down. And then it's going into this file dispatcher IMPL read 0, right? So by looking at this, it's becoming very obvious that there was some back-end slowdown at Oracle is happening. So that's why all the transactions are getting stuck. Immediately you can get to that problem. Friends, this is probably in this entire session, if you want to take one thing away, probably it is this one. That is, look at the last executed method and group them. And if you see multiple threads are there, it means it's a clear indication there is a problem going on, right? Because typically, whenever there is a bottleneck, all the threads are going to go and then going to be stuck in one point. So that's the point you want to be focusing investigation. This will facilitate you identify several problems. Okay. So now let's move on to the second tip that I want to share with you. Friends, one common problem that we all confront in our production environment is CPU spikes. So you will see our application CPU spiked up to 80-90%. We didn't know why. How to troubleshoot the problem. I'm going to be sharing with you a very effective and a very non-intrusive approach to do right now, right? So friends, and friends, one more thing before I go. See, whenever a CPU spikes up, there's only one reason for it. There's only one reason for it. The reason is a thread, your application thread or multiple threads, they start to execute your program code continuously. Only when your program code gets executed continuously, when threads gets very, very busy, keep on executing multiple lines of code, that's when the CPU is going to spike up. So whenever the CPU spikes up, our very first job should be to identify which thread is causing the CPU to spike up. Because my application has like a 300, 400 threads. From that, how am I going to isolate and find what are those 2-3 threads which is causing the CPU to spike? That should be my first step in diagnosing the CPU spike. For that, my friends, here I'm going to be sharing with you a very nice trick, right? Friends, we all have used this Linux command top, right? I think most of us have used this Linux command top. So when you issue this top command, this command is going to display all the processes running within that container or on the server. And then what does that each process consume? How much CPU and memory that each process consume is going to be reported to us. Friends, this top command has one secret option. Not that many developers know. Today, we are all going to learn that. It is this command, top -h, uppercase H, -p, and give your process ID, give your Java process ID, which is suffering from iCPU spike. When you give that, this top command is going to display all the threads that is running within this particular process and what is the CPU and what is the memory that each thread is consuming. You see, this application CPU consumption is at 100%. And in this 100% CPU consumption, there's one thread, which is the ID 31306. This is a thread ID. It is consuming 69% CPU. Another thread 31307 is consuming 65% CPU. And the third thread consumes 64% CPU. All other threads are consuming only 0% CPU. See, friends, you may wonder why it is 69 plus 65 plus 64 is not 100. It is kind of a 200. It is 200% because this machine was running on a 2-core machine. So it can go up to 200%. Right? That is the reason. So now if you see, only these are the 3 threads which are the culprit. All other threads are consuming only 0% CPU. So this is very clear indication that these are the 3 threads which is executing, which is consuming the CPU spike. So now, out of my hundreds of threads, just with this simple command, I am able to isolate which are those 3 threads which is causing the CPU to spike. Now, having known this thread ID, what I can do, I can take this thread IDs and then in my thread dump, I can go and look. In my thread dump, I can see, oh, this thread ID means that's going to show me what is the thread, which then I'll know what is the stack trace it is executing. So once I know what is the stack trace, then I can solve, oh, these are the lines of code that is causing a CPU to spike. And this is one reason why I'm recommending to capture this 360-degree data, right? Capture this 360-degree data. Because look at the script. What does it do? It captures you 3 snapshots of thread dump. Along with that, it also captures this top dash h as well. So you don't have to go and manually capture this top dash h. And also a lot of times, maybe the developers are here in this call. A lot of time when the production problem happens, because of the heat of the moment, the SRE team, they go and recycle the JVMs without taking these dumps. But now if you say, SRE team, make this as part of your process, before recycling, capture me this data. So now with this data, we can go, we'll have all the information. We're going to have the top dash h and also the thread dump. Having with this information, we can easily say which is the threads causing the CPU to spike. So now let's look into a real case study, right? So this is a CPU spike that happened in a trading application, in a real trading application. So what you can do to this fastThread is, fastThread tool, you can come and then you can, when you're uploading the thread dump, in the thread dump file itself at the bottom, you can attach the top dash h output if you're manually capturing, and then you can upload it, or you can do that. So once you do, here is that analysis report which is generating. So now here you're going to see a section called CPU consumption by thread. See here it displays, now start to display what is each thread is doing and how much CPU it is consuming. How much CPU it is consuming, this is coming from the top dash h command. And this is coming from the thread dump. The fastThread tool marries these two information and presents you this kind of a report. So now here from this, I can see there's this thread called web container 18 is consuming 60.9% of CPU. Now let's look into that. So let's also see there is also other thread. These are all the other threads. They are also consuming 26%, 26%. But let's just focus on the most high consuming CPU consuming thread. So now when I click on the stack trace, I'm coming here. So here the stack trace tells, okay, this application, this trading application was running on IBM WebSphere server. And now it's starting to execute that application code. And now this application code is calling this weak hashmap.put. So this is the method, what the thread is executing. And that's when the CPU is going to the 60.9% consumption, high consumption. Friends, hashmap is not a thread safe implementation. In JDK, hashmap is not a thread safe implementation. When multiple threads try to do a concurrent get and a put operation on the same hashmap, then the threads will start to go on an infinite loop. The threads will go on an infinite loop. When a thread goes on an infinite loop, that means the CPU will spike up. So you may wonder, oh, why this is a bug? Why this is part of why the hashmap is behaving like this? See, hashmap is very clearly in the documentation they mentioned. This is for a non-thread safe implementation. If you want to go for a thread safe implementation, use a concurrent hashmap. That is the data structure you want to use. So moment they saw this, this trading application engineering team, they replaced this hashmap with a concurrent hashmap. Once they changed it, then the problem went away. With this, you can isolate CPU spike problems very easily in a non-intrusive manner. Okay. So now I'm moving on to my third tip, which is blocked threads. Okay, friends, this is another thing. So when you're analyzing a thread dump, you want to be focusing on the threads which are in a blocked state. So you take a thread dump, you say you're opening a text editor, then you want to see what are the thread states of each thread which is in a blocked state, and you want to focus attention on the threads which are in the blocked state. Why? Right? For that, we need to understand what does a blocked state means. What can cause a thread to go into blocked state? Friends, there are engineers in this call, so you are very familiar, but we also have performance engineers and site reliability engineers in this call. So for them, a quick introduction. In Java, there is a keyword called synchronized keyword. I can mark any method with the synchronized keyword. When I mark this method as a synchronized keyword, what happens? When I mark this method as synchronized keyword, that means only one thread is going to be allowed to invoke this get data method for that object at any given point in time. Only one thread will be allowed to go, right? So all other threads will not be allowed to go. So let's take this example. Let's say thread 1 now comes. JVM is going to check. Since it's a synchronized method, it's going to check whether any other threads are executing this method. No threads are executing this method. So then this thread 1 is allowed to move inside. Yes, go and execute. Now thread 1 now comes here. And now it starts to execute the do something method. Now let's say at this time, a thread 2 comes. A thread 2 is coming. Now JVM will check. Is any other thread trying to invoke this get data method? Yes, already thread 1 is inside this get data. So now thread 2 will not be allowed to go inside. So this is when the thread 2 is going to go into the blocked state. Right? It's going to go to blocked state because it's not allowed to progress forward. So what if this do something takes very long time to complete? It can happen, right? Because what if this do something is a poorly implemented method, it's going to take very long time to complete. Then all those time, this thread 2 has to wait. It's going to be a block state. Friends, what is a thread, my friends? At the end of the day, behind every thread, there is a customer waiting. Because this thread 2 is nothing but a customer request. That means the customer is waiting. If this thread 1 is taking very long time to complete, then that customer is not going to get response. What if this thread 1, this do something method is very poorly implemented, it takes very long time to complete. So another customer request comes, it's going to be stuck. Another customer request comes. So like this, multiple requests are going to come, they're going to be stuck. So you want to be focusing attention on the blocked threads. Maybe because it's blocked, they're not able to progress forward because some resources taken away. Okay. So pay attention to blocked state threads. So now, friends, how is this going to look in the thread dump? How is it going to look in the thread stack trace when this happens, when this scenario happens? Let's look into that. This is how the thread stack trace is going to look like. Say here the thread 1 has got the lock and it has entered, and thread 2 is waiting to progress forward. So now this is how the stack trace is going to look. Okay, I think my arrow is a little bit off because of this presentation mode. Maybe I'll exit this presentation. Okay. Actually, the arrow should be here. Yes. Okay. So look at this. This thread 2, this is the thread which is now trying to enter into this get data method. Look at this, what happened. It's going to say, it's put in the blocked state. You see this in a blocked state. But now, here it's going to say, see, it is saying it is trying to enter this get data, but it's blocked. And it is blocked because of this lock, because some other thread has taken this lock. Look at this. We want to focus on this ID. See, this is all a little bit tedious to do manually. That's why the tooling is going to help, but just still learn the manual approach. See, here it says, it's saying waiting to acquire this lock, BAA 5498. But now, look at the thread 1. This is the stack trace of the thread 1. This is the thread which has acquired the lock. Look how it's going to look. This thread, you see, it is saying it has locked. It has locked. It has able to enter this get data method. It has gone to do something method. So look at this. Here it says locked for this. And whereas this guy is saying waiting to lock. But it's on the same lock. You see, it's the same lock. BAA 5498, BAA 5498. That is the difference. So this means this thread 2 is now a victim. He is not able to progress forward. Okay. So now, so whenever in the blocked state methods, whenever you look in the blocked state, let's see for which lock it is waiting. And then see who is holding on to the lock. Then you can understand the full story. Right? It's just connecting. It's a kind of a detective work a little bit. If you want to see this, I have to first go and look what are the blocked state thread and see where it is waiting to lock. And now see who is holding on to the lock. Then follow this thread. Then you will see, okay, where it is actually stuck, where is the bottleneck is happening. You can do this manually, or there's also, if you do it in the tool is going to paint this as a transitive dependency graph. Let's look at this with a real world example. So there was a concurrency issue. There is this blocking issue that happened in a leisure travel service provider. they make that airline ticket reservation. So that application was running into this concurrency issue. Now let's look into that report. Okay, so now coming along, see here it was very sick. So there are a lot of issues. See here, there is a section called blocked threads graph. Whenever the threads gets blocked, the tool is going to paint you this kind of a transitive dependency graph, right? This shows these are all the threads which are waiting to acquire the lock. See here, it shows in fairly simple English. It says this method is what blocking 646 threads. So you can just directly go and see what's going on here. See here are those 646 threads. If you want to see what is the stack trace, we can just need to click on this. When I click here, I can see, oh, okay, this is the stack trace. It is trying to acquire this lock, waiting to lock, but it's not able to acquire the lock, so it's getting in the blocked state. Friends, so just a little bit context. This might be surprising to several of us. See, as developers, in our code, we try to generate random UUID, universally unique identifier numbers. To do that, as Java developer, we use this API called UUID, random UUID method. When we invoke this, a lot of developers, we don't know, but this is actually a synchronized method. That means only one thread is going to be allowed to go inside this method. The other threads will be put to the blocked state. If random number generation is going to slow down, then all the threads which is coming to invoke, they are also going to have be put in the blocked state. So that's why you can see all the 646 threads are stuck, not able to progress. And this is the guy, culprit thread, which acquired the lock and he did not release it. Because he did not release it, their 646 threads are stuck. That means what? 646 customers are not getting response at this time. Now when I click here, now I can see the stack trace of what's going on. Okay, you can see this thread, it acquired this lock. And now when it tries to generate a random number, it is not able to generate. Because see friends, the JDK delegates the call to the underlying kernel to generate a random number. If there is a lack of random number, there's hash algorithms, which is there from the kernel side to generate. If there is a lack of that entropy, then the random number generation will slow down. So that's what was going on. By patching the operating system, they were able to resolve the problem. But at least this is helping me to tell where the problem is happening. Okay. Okay. Now, let's move on. The next tip that I want to share is look for deadlocks. Friend, this is pretty rare to happen. It's very rare to happen in Java applications, but it can happen, right? See, what can cause a deadlock? What can cause a deadlock? Friends, I want to give a real world analogy so that you can better correlate it. See, friends, let's say there's two trains, train A and train B. Both of them are starting at two points, but let's say they are starting on the same track. There's only one train track. They both are starting. It's accidentally they're starting. Then what's going to happen? What's going to happen when they come close to each other? See, this is a very bad example. It shouldn't happen. This shouldn't happen. But when they come close to each other, that means both the trains wouldn't be able to progress forward, right? Because it wouldn't be able to progress forward. The reason is, look at this, because this train is in a track, is holding on to this track, and it wants to move forward. But this other train is holding on to the track where this train A wants to go, but it's not able to move forward because where this train B wants to go is held by train A. Both of them wouldn't be able to move forward. Both the trains will be stuck there because there's only one track. So if this happens, that means it's deadlock. Both the trains cannot move forward. At this point, you have to recycle the JVM to recover from the situation. There is no other go, right? So how does it look in the thread dump report? How does it look? It will in the actual thread dump report. This is how it will look. Both the threads will be in a blocked state. You see, both the threads will be in a blocked state. But the IDs in which it has acquired the lock and waiting for the lock is going to be in the reverse sequence. You see this thread 0. This is acquired this lock 1970. It's waiting to acquire this lock 1980. Whereas this thread 1, the sequence is exactly vice versa. It has acquired this lock. It's waiting for this lock. So when you see this pattern, it means a classic deadlock. These two threads are in deadlock with each other and they wouldn't be able to move forward. Okay. So now let's look at this with a real world example. So this problem happened in an open source application called as Apache PDF box. So this is a library what several Java developers uses to generate PDF documents from their web applications. Look at this. See, when that happens, the tool flags it. Oh, there's a deadlock. Application is suffering. It's a fatal error. You want to look at this. So here is that stack. See, it prints a stack trace. So this is a thread 1, which is in blocked state. You see it has acquired this lock, but is waiting to acquire a different lock. Whereas the another thread is doing exact reverse sequence. So both the threads are in deadlock. So having noticed this, then the problem was happening in the Apache PDF box library. When this was reported, then they had a latest version where they addressed this problem. And then once they upgraded, the problem went away. Okay. So now I'm moving along. Friends, the next pattern that what we want to be looking at in your thread dump analysis, look for threads which have a lengthy stack trace. That is, if a thread which has a very large stack trace, like, I don't know, 700, 800 lines, that means you need to start investigating, because a lengthy stack trace indicates that this thread is either going on a loop, or it is, whenever a lengthy stack trace also indicates it's consuming a lot of resources, because it's now going through multiple methods, creating multiple objects, a resource intensive operation. So you want to be paying attention to it. Several times it may not be a problem, a lengthy stack trace, but it is worthwhile to investigate it. So here, let's look at a real case study. See, here there is a section called, see friends, the tool can do this for you, but you can also look at it manually, right? You can open a thread dump. It's a simple text file. You can look at it. So here you can see there's a threads with thread stack trace. Here it tries to do a grouping. Here it says 2 threads are having more than 400 lines stack trace. Look at this. Here it raises a warning. So I can click here and then I can see. Here you see, friend, this is one of the thread. There is a thread called the EJB default 5. Look at the stack trace, how lengthy it is. You can see it goes and goes. But actually what was happening was, if you see, if I'm searching for the string proceed method, this is being called like 328 times. So if you see, it is going on some kind of a recursive loop. So so then you have to check whether it is intentional, whether you want to do it or not. Okay. And friends, the next tip, the 6th tip I want to share, you also want to look for the threads. In the threads, exceptions gets thrown, right? Our application throws out of memory error, stack overflow error, null pointer exceptions. Those all gets thrown. Those all either results in a kind of a system level outages or a functional problem. So you want to investigate what are threads which is throwing exceptions and look at it where it is happening, right? So here I want to show you. Here is an example, a real one. So exception, there's a section called exception. So here it shows what are the threads which is having exceptions will be highlighted for you here. So here you can see there is some thread which is coming, it is having a transport level exception. So then I can see where all this exception is happening. Those threads are highlighted. This is a thread, and these are the threads which is having exceptions. Then you can take a look at it. Okay, here it is coming. It's trying to do some Active Directory authentication, but it's resulting in an exception. This is not that important. but just to be aware, to be advised, just keep it in mind when you're looking at thread dump. Okay. Friends, the next tip that I want to share, this is fairly an important one for you to take into account. That is, compare the thread states across dump. See, I told a thread dump is just basically a photograph of your threads. So what is a photograph? Photograph is, it means it is a image at a point in time. It's not a video. Video means it just keeps on, it's a multiple accumulation of multiple photographs together, right? I mean, just at one point, what's going on, which is good. Having a thread dump taken at one thread dump is good. But friends, in general, it is a best practice. I want to share. In general, it is a best practice to capture at least multiple thread dumps at regular interval and do the analysis. So that I can see, okay, at 10 a.m., the thread was at this position. At 10 seconds later, if I want to take see, the best practice I would recommend is for most business application, take at least 3 thread dumps in a gap of 10 seconds in between each other. So you can add more thread dumps or minimize the gap based on your need, but typically taking 3 thread dumps at a gap of 10 seconds is a good thing to do, is one of the best practice. Because I know, okay, at 10 a.m., this thread was at this point, in this state, it was executing this method. 10 seconds later, if this thread didn't move anywhere, it is still there, it's indicating me it's stuck there. Or if thread has moved someplace, that means it's still okay, the thread is progressing. So looking at multiple thread dumps gives me a picture of what's going on in the application. You can collect multiple thread dumps and then you can upload to the fastThread tool, either as a zip file. You can compress a zip file and upload, or you can upload it as individual tools. Say, you can come. I can say I collected the first thread dump file. I can select it, put it here. I can say add file, second thread dump file. I can do like this, keep on adding and do it. Or I can compress all of them into one zip file and then upload. Right? Okay. So now, I'm sharing some of the best practices. Capture multiple thread dumps at regular intervals, 10 seconds, 3 thread dumps, and do the analysis. And then the second best practice that I want to share is, friends, a lot of time, what happens is a thread dump is not captured when the performance problem is happening. A lot of times I've seen, we ask support engineers to take a thread dump. What if the support engineer has recycled the JVM, and after recycling, he's going to capture a thread dump and give it to you? It's not going to be helpful. When the patient is in the serious pain, at that point we want to draw the samples, not when the patient is healthy, right? So this is a thing you want to make sure before you recycle, you want to capture the dumps and then do the analysis. And then also, just thread dumps is not just enough. Having the 360-degree artifacts is going to be very nice to see the comprehensive analysis, because that 360-degree artifacts takes the network data. If there's any network slowdown happens, I can look at it. Storage data, we can look at everything. Okay, and then another thing also, you want to archive the thread dumps securely, because thread dump contains several confidential data. Because thread dumps will contain your code stack trace. That means it's going to tell what are the third-party jars, third-party libraries you are using. And sometimes it also contains the IP addresses. Those are all classified as a confidential data. So you don't want your thread dumps to be hanging everywhere. It has to be archived and maintained properly. And sometimes when JVM becomes very sick, it's not going to respond to our general JStack kind of a tool. JStack, JSEM will not work. You have to use JStack with -F, forced option to take a thread dump, right? So these are some of the best practices that I want to share. Okay. So now, having said that, let's look into this one, comparing the thread states across the dumps, how that's going to facilitate us, how that's going to help us. So now, here is an example. So this was a real data which happened, a real problem that happened in an airline application, which makes ticket reservations. So their JVM had a CPU spike. They had a CPU spike. I told earlier the best practice to isolate the CPU spikes is by taking the top dash H. output and then looking into that. That's what we discussed earlier, right? But this team, because they didn't capture the top dash it, they had only a thread dump. They have only few snapshots of thread dumps. If I don't have a top dash H, is there any way that I can isolate the problems? Yes, you can. But here's an example of that. So now let's look into that. See, this airline JVM, they capture like a 3 thread dumps. One at 10:37:28, 10:37:38, 10:37:48. In a gap of 10 seconds, they capture. So here's each individual thread dump analysis. But here at the very top, there's a comparative summary. So this compares all the thread dumps and then gives you the output. Okay, here it shows, okay, at 10:37:28, how many threads were there? At 48, are they fluctuating? No, they're not fluctuating. What are the each threads? What states they are? What are the different thread pools? Whether are there any fluctuation? But here, what does this tool does is, the tool now looks for runnable state threads. See, runnable state thread means they are threads which are executing some lines of code. So here it looks at them and sees whether the thread is in a runnable state continuously for all these 30 seconds. Yes, for all these 30 seconds, these 9 threads are stuck in the same method in the same state, in a runnable state. If a thread is in a runnable state, it means the thread is executing some lines of code. But here, if it's executing lines of code, it should have progressed. It should have gone to other methods, but it didn't progress. You were just stuck on the same method, same line of code. So the 9 threads doing like that. So now if you click on the stack trace, here you can see this is all those 9 threads. They were in this itinerary segment processor, line 380. That's where they were. So what's going on there was, this application had a source code. Yes. So this application at that line 380, the source code was something like this. While some condition, they had a code like this. This condition, what happened was, for some reason, for certain data set, it always evaluated to be true. So while true, it had something. So that means the thread was, while true, if it becomes true, means the thread will go on an infinite loop. The thread will constantly keep on executing it again and again and again and again. Then the CPU will spike up. That's what was going on. So then once they saw, they were able to precisely see this is the line, exact line, where the threads were all stuck. This is the exact line. So now I know I can go and look into this line to see what is going on. So that was able to isolate and give me the problem. Okay. So now the next pattern, the next tip that I want to share is, look at the GC thread count, the garbage collection thread count. Garbage collection threads will be reported in your thread dumps. So, friends, there is this famous English saying, too many cooks spoil the broth, right? If too many people are in the kitchen working on the same dish, the dish is going to get spoiled. Similarly, if there are too many garbage collection threads, they tend to degenerate your application performance. They tend to degenerate your garbage collection performance. Friends, a lot of developers, engineers, we don't know how is the GC thread count derived. How does the JVM knows how many GCs I should create for this application? Friends, to explicitly specify how many GC threads we need to use these JVM flags, parallel GC threads, and give the count. GC threads count and concurrent GC and give the count. This is going to explicitly configure the GC thread count. But if you don't give, the GC thread count is derived based on the number of CPU cores that is there on the machine. Let's say, suppose you are running on a 128 core. There's a mathematical formula. You can look into that mathematical formula, what that is. Here it is. Based on number of processors, it's going to derive. So if you are going to be running with 32 CPU cores, you're going to end up having 23 parallel GC threads and 6 concurrent GC threads. Say, hypothetically, let's say you're running on a 128 CPU core machine. That means you're going to end up somewhere like 100 plus threads. But what if in that 128 CPU core machine, what if you're running 5 JVMs? Or this problem is getting more pervasive in the container world. The underlying host may have 138 cores, but what is allocated for your container may be limited. But it's if JVM is going to derive from the underlying operating system, then you're going to end up having more GC threads. If you end up having more GC threads, then your response time is going to degrade. Right? So here is a real example where it shows the over allocation of GC threads. So there is a section called GC threads. See here, this application ended up having like 145 garbage collection threads, which is way too much. It was causing a lot of pauses in the application. So you want to, how do I know what are the GC threads? Look at the name. The name will say it's a GC thread. Based on the name only, we get to derive that. Okay. So now I'm moving on to the last tip, right? So friends, look for the thread activities within the thread pool. See, our applications have multiple thread pools, right? See, we do have a servlet container thread pool, which is at the very forefront. And we do have a separate quartz thread pool to execute certain batch processes. Maybe some applications have certain thread pool to make a backend calls. So look at the thread activities within the thread pool. See, I want to show this example. Sometimes if the thread pool can exhaust, here is a real example. What happened? This application was running on a containers Kubernetes, but all of a sudden the pod will get recycled. The pod was constantly getting recycled in the Kubernetes environment. They didn't know why. The thread dump revealed it. When the thread dump was caught, that's what we're going to look at it. Let's look at this. See, here, there is a section called thread pools. So our application has multiple thread pools. Here, look at this. One of the thread pool, here name is called as a web container thread pool. It has like a 50 threads. In this 50 threads, 96 threads were busy. They're doing some other work. Say they're in a runnable, they're doing other work. So at some point, it goes to 100%. If all the 100 threads are busy doing some work, that means what happens? This web container is the very forefront thread pool to service all the incoming requests. If they all get busy, that means that when the health check request comes, when the Kubernetes health check request comes, there are no threads to process. So the health check fails. Then they thought, oh, then this pod is not unhealthy, then it goes and recycles. So this application may have, like I say, it has like 800 plus threads. Out of them, if you see 510 are waiting. But this is the very forefront thread pool, and all of them are busy. Since there is no more threads are available, the pod was timing out. So you want to look for each and every thread pool and how the threads are behaving within that. So this will help us to tell what production problems are surfacing. Okay. So friends, okay. So friends, I would like to thank, with this I'm coming to an end of my webinar. But I will be here to take questions. What are the questions that have come in the chat? I'm going to be looking and responding. But whoever wants to sign off, you guys are most welcome to sign off. So thank you, my friends, whoever attended. I hope the session was helpful. So for whoever attended, we will be sharing an ebook will be sent to you, which contains several performance tips that you can take it and apply. So, and this is a monthly webinar series we are conducting. So feel free to join based on your availability. Okay. Thank you, everyone.